Good morning, everyone. Today we will look into uh, the correlation between the S plane and the Z plane. We have already discussed, but we will be discussing about some of the features which will be important for us while we will be discussing about the filters at the later stages. Okay. So, as we have discussed, if you look into the S plane over here, as we discussed that there is a real axis and there is an imaginary axis, and this imaginary axis we are basically having the frequency component associated with it. Okay, then when we try to map this S plane with the Z plane, we have seen that the left hand side plane, it mapped within the unit circle. The right hand side plane, it mapped outside the unit circle. Okay, whereas this imaginary axis, it got mapped onto the unit circle itself. So over here, if you see, it has been given that sigma is equal to 0. Okay, and we have already discussed that the imaginary axis is associated with the analog frequency. Okay, whereas Z plane, it deals with the digital frequency. So this analog frequency, it gets mapped onto the unit circle. That means the analog frequency, it is being mapped with the digital frequency. Okay, however, there is a problem over here. The problem is that the analog frequency, it can vary from minus infinity to infinity. Don't disturb the class if you are coming late. Just come in and sit down. Okay. Whereas when we talk about the Z plane, so what we discussed, that we start with 0 degree and we end at 2 pi. Okay, we start at 0 degree and we end at 2 pi. Okay, so the maximum frequency component that can be mapped from the analog frequency to the digital frequency would be in the range of 0 to 2 pi. However, when we talk about the digital frequency, we talked that there are two types of frequency. What are the frequencies? The first frequency is the sampling frequency, which is greater than the FM, which is the maximum frequency of the signal. Okay. Now, when we talk about the systems, this FM stands for the maximum legal frequency that can be processed with the digital system. Okay. So, if we look into this again from here, if we look into the our Nyquist equation criteria, which says Fs equals to Fs is greater than equal to 2 of Fm. That means Fs, as I already told you, it will be mapped at 2 pi, and at pi will be having the Fm. Okay. So what will happen? So if we see, if we start from 0 in the analog domain, from 0 hertz will be coming to the FM. Then from the FM to whatever will be the sampling frequency, we will go over there, and after that frequency, the frequencies will repeat. Similarly, the frequency will repeat when we go in the clockwise direction. Whether we go in the anti-clockwise direction or we go in the clockwise direction, doesn't matter. The frequencies, they will try to repeat. They will be repeating itself in both the positive domain and in the clockwise fashion and in the anti-clockwise fashion. Okay, so that means what will happen is that the mapping of the analog frequency to the digital frequency, it is basically a many to one mapping. Okay, so many analog frequencies, they will be mapped to a particular location in the digital frequency domain in the Z plane. Okay, so this is one of the main problems with the system. Okay, this is one of the main problems with the system. System means a digital system. Okay, because we are not able to accommodate all the frequency components together. So there is a limitation of accommodating the digital frequency. Okay. Now let us take the example of an ECG signal. Usually the ECG signal, it is having frequency components varying from 0.5 Hertz to 100 Hertz. However, in some books you may find that it is 120 Hertz. So it doesn't matter, for the sake of the simplicity we will go with 100 Hertz. Okay. So as per the Nyquist criteria, what should be the critical FS? The critical FS would be 200. Okay, the critical FS would be 200. So if we look, go back into the Z plane, so the location of FS is fixed, so it is 200 Hertz. So when we have given 200 Hertz over there, so FM would be at pi, that means at 100 Hertz would be at pi. Okay, now when we do this, what is happening? If you look into the frequency spectrum, what is happening? The low frequency to the high frequency component, we have got the, this is 0 to pi, right? So we have got this component, and after that pi to 2 pi, that means pi to 2 pi means FM to FS, we will be having the repetition of the frequency components. Okay. So what is happening when we try to acquire some ECG signals and all this thing? In this regard, if we use, especially when we are doing some teaching experiments in the laboratories, we use low cost data acquisition systems. We use low cost data acquisition systems, and in our previous class I have told that due to the non idealness of the components, of the electrical components, the high frequency components which are present somewhere over here, they get mixed up with the low frequency components. So we get some mixing up over here, and this mixing up, it is regarded as the spectral leakage. Okay, so leakage means it is unwanted. Okay, we did not want, but it happened. We maintained all the ideal conditions, but however, due to the non-idealness of the electronic components, there would be some mixing up. So this is called spectral leakage. Another term which is also regarded as the Nyquist aliasing, which happens if you do not follow this Nyquist rate equation. Nyquist rate equation. If you do not follow this equation, so what will happen basically? Again, it will repeat somewhere like this. Okay, so when we are not following this, over here also, let's see, there is a mixing up of the frequency components, and this is called aliasing. This is called aliasing. the results of aliasing and spectral leakage are similar. Okay, that these systems, both these phenomena, aliasing and the spectral leakage, will lead to the corrupting of the original signal what we are acquiring. Okay, so if there is a corruption of the signal, that means the information content what you will be getting, it's totally falsified, it is not idle and it will give you wrong information. Okay, but both the phenomena they are happening due to separate reasons. Spectral leakage, it is happening because of the non-idleness of the electronic components, whereas aliasing, it is happening because we are not following the Nyquist rate criteria. Okay. Now, when we talk about this spectral leakage, as I told you that while acquiring the ECG, we have the highest frequency, say 100 Hz. Now, what happens is that under normal circumstances, the FS should have been 200 Hz. But since we use low cost data acquisition systems for teaching purposes, it has been found that the FS should at least be 10 of FM, 10 times of FM. Okay, that means kitna? 1 kilohertz. The sampling frequency will be 1 kilohertz. Okay, so when this is happening, if you look into the Z plane again, 1000 hertz, it comes over here, and here what will be getting? 500 hertz, right? So where will be my 100 hertz? Because my frequency component is within a very narrow range, right? So where it will be? If you see 100 hertz, it will be at a region of 100 hertz by 1000 hertz multiplied by 360 degree. So 36 degree. So somewhere over here we will be having our 100 hertz. Okay. Now when we are having this, so if you see, because this frequency is again repeating, so we will be having another here. So if you see, in between these two bands, there is such a large band in the digital system which is remaining unoccupied. We are not able to use this frequency band even though it is available to us. Okay, so this is called oversampling. This phenomena is called oversampling. Oversampling means when we sample a signal at a higher frequency than that required in the Nyquist rate. Now, what is the problem with the oversampling? The problem with the oversampling is that, what do you mean by sampling frequency of 200 hertz or sampling frequency of 1000 hertz? That means for 200 hertz sampling frequency, in 1 second you will be having 200 data points, whereas in 1 kilohertz you will be having 1000 data points in 1 second. Suppose you have to record a data for 5 minutes. So see the number of data points that will be generated. So data points need to be stored again, right? Now you need a large storage point, and when you are having large number of data points, if you want to perform any signal processing, what will happen? The computational burden will also increase. Okay. So if you see oversampling, it is helping us in eliminating or in preventing the spectral leakage and also the aliasing, because it is meeting the Nyquist criteria. Okay, because our Nyquist criteria says less than greater than equal to 2 of fm, so it meets our Nyquist criteria. So both the things it is preventing spectral leakage and the aliasing, but the problem arises, it is generating a lot of data part which is not desirable. Okay, which is not desirable. On the other hand, when there is aliasing, as I told you, we are not following this Nyquist rate. That means Fs is less than 2 of Fm. Under that conditions, lower samples are being generated, lower number of samples are being generated, and that is called undersampling. So that is called undersampling, oversampling and undersampling. Right? Now, due to this oversampling, this blank region, what we get, it is called dead zone. And also in my class I have told, it is not last class, maybe one of the classes I told you that it is also regarded as null zone. Okay, yeah. So you can see how the things are unraveling as we move forward. Now, since in our what do you call, in our labs, teaching labs, most of the teaching labs, you'll be having mostly low cost data acquisition system. Low cost means they also cost around 25,000 to 30,000 minimum price of the data acquisition system is that much, 20,000, 25,000 to 30,000 or even more. Okay, that is not a small amount. So what to do? Because you have no other choice but to work with that. So the better idea is that we sample the signal at a higher frequency, say 10 times of FM. Okay. Then we can downsize the samples. Okay. We discussed about we discussed about bolo, decimation of the, yes. So various yeah. So downsize means we decimate the signal in particular rate. Okay. So when we do that, what happens? We are again, because we cannot change the time. Time will be same. Okay. So what we are doing? We are reducing the sampling frequency components, because we are artificially manipulating the sampling frequency. Okay, so in a single system, if you see, there are two sampling frequencies. There are two sampling frequencies. So such kind of system where there are two or more number of sampling frequencies, and when we are using those signals for the processing, it is regarded as multi-rate DSP. Okay, because we are having multiple sampling rates, multiple sampling rates. Okay, in this example I have shown that I we acquire the signal at a large at a greater sampling rate, and then this downsize the sampling rate by decimating some of the data points, and we get a lower sampling frequency signal. This is one of the way for the multi-rate DSP. The another way is that you do the sampling at a normal rate, and due to some reason, say for example, to have a better understanding of the frequency component, we need to oversample it. Okay, we need to oversample it. Initially, what we said while doing the numericals, we said that we pad zeros. Okay, but padding zeros may not help us in many of the things, because our signal resolution, it is not increasing. So if you want to increase the signal resolution, then what you need to do? So in that case, what happens is that we have a lower sampling rate, then we use an interpolation function to find out the envelope of the signal. Okay, to find out the envelope of the signal, and using that envelope signal, we perform sampling again in the digital domain itself. Okay, because here we are already sampled the signal and digitized it. Then we want to increase the sampling rate, and for that purpose we have used an interpolation function. Because while using the interpolation function, say for example, I have a sinusoidal wave like this. Okay, now if I have to get this intermediate value, how will I get? I will not get. If I use interpolation function, what it will do, it will create an envelope like this. It will trace the data points. Okay, now this data point is basically a function. So now at this location, what is the expected amplitude, I can get it. Okay, so at the next stage we can do the sampling after implementing the interpolation function onto the data point, so as to get the envelope of the signal. Okay, once we get that, so we again have increased the sampling frequency from a lower sampling frequency. Okay, from a lower sampling frequency we have gone into the higher sampling frequency, and this is another type of multi-rate DSP. Okay, but you have to be, in the second case, you have to be very careful that the signal that you are using, that signal should not be aliased. If the signal itself is aliased, that means the signal itself contains wrong information, and whatever you do oversampling, how much oversampling you want to do, if the original is corrupted, the final version of the signal what you will be getting, that will also be giving you corrupted information. Okay, that will also give you corrupted information. यहाँ पे if you see this dead zone I have shown, so when you increase the sampling here, so see this is the dead zone, and if you consider this 2 pi region, so dead, say it is, suppose here it was 36 degree, and here it was this thing. So this region, if you see 0 to this one, we had the frequency components. Then from this region to this region we have the dead zone. So we have this dead zone over here, and then again we had the frequency component repeating itself. So this is just the representation of what you call linear representation of this one for better understanding. That's it. Okay. Any questions till now? Lower sampling frequency to. Hmm. Hmm. It depends on your the utility. That's why I gave you two reasons. In the first reason, in the first case, what we did, we oversampled and we downsampled. Okay. So when we downsample, if you want to store it in that condition, that's perfectly fine for us. In the second case, I gave you told you the example that you have under normal you have followed the Nyquist rate, but due to some reason you need to oversample it. One of the example is, suppose you want to look into the frequency spectra of the signal. Okay, so what happens in DFT? If you are having only 4 point yeah, signal components, you'll be getting 4 point DFT. But if you just sample it to say 16 point, so you will be getting frequency components for the 16 point. So you will be able to see the frequency axis in a much better way. If you remember my DFT class, I told you basically when you are doing the DFT, scene is already present and you are looking at the window. Now the number of data points are number of the slits which are available within the window through which you can see the scene. The number of higher the number of these slits it will be there, the better will be your visualization of the scene. The same thing happened over here also. Now, if you look into the comparison, just a small, uh, if you want to summarize it, basically what I want to say is that when you go from the Laplace domain, which is having frequency component from minus infinity to infinity to the z plane, we have many to one mapping. Then, if we want to try to design some filters, so what are the considerations? What are the similarities and dissimilarities? If you look into the S plane, number of poles should be greater than equal to the number of zeros. In Z plane, while designing the digital filters, there would be no change in the criteria. Same criteria would be there. Now, in S plane, we have poles in the left hand side of the S plane. However, in Z plane, we have to place the poles inside the unit circle. Okay, zeros in the S plane can be put anywhere. In the Z plane also there is no change. We can put the zeros anywhere. Okay. Now coming to the next topic, the digital filter designing. This is seen. This is similar to what we discussed in our Laplace transform or S plane lecture. Okay. However, the over there I told you the point P, it was on the imaginary axis while we will be trying to look into the amplitude response or the phase response. Herein, where this point should be on the unit circle. See, over here, right? Now, rest all of the derivations, they are the same. Okay, same means over there we were dealing with HS because we were in the S plane. Here, that HS will be HZ because we are dealing in the yeah, digital domain or the Z plane. Okay, so this is again equals to, I think Pz by Qz. We use the two polynomials. Whatever nomenclature you want, you can use it. So you have this Pz and the Qz nomenclature, and this is equal to Bn, which is again the frequency independent gain, and then we have these polynomial values. So herein in the numerator, the roots of the polynomial pz, they are the zeros, whereas the roots of the denominator, they are the poles. What happened? Feeling sleepy? Huh? His eyes are totally closed, almost closed. Now again, like same way, we get into the polar coordinates. Okay, if you look into the modulus of the Bn, frequency independent component, multiplied by product of the distance of the zeros to the point p theta. Here it is e to the power j omega t, which is again onto the frequency axis. Similarly, product of distance of poles to j omega t. And phase again, if you see, phi 1 plus phi 2 plus phi n minus of theta 1 plus theta 2 plus theta n. So sum of zero angles to e to the power j omega t minus sum of pole angles to e to the power j omega t. Again, if you want to calculate the phase, if you see, you have to draw a parallel line with that of the x-axis, and then towards the anti-clockwise direction you need to go. Okay. So this you need to remember. Now let us take an example. The example is that we are given with a transfer function hz equals to 1 by z minus 0.9 phase 0 degree. Okay. Now from this polar coordinate we can convert it into the rectangular coordinate, and it is the easiest way. Okay. Now this equation 1 by z into 0.9 can be multiplied with z inverse both in the numerator and the denominator, and we get a term z inverse divided by 1 minus 0.9 z inverse. Okay. Now both these equations are valid, but you have to use it for different purposes. Okay. Say for example, when your equation is 1 by z minus 0.9, it will be used to find out the locations of the poles and the zeros. Okay. So in the zeros there are no z terms. Okay. So we will not touch it. In the denominator we have z minus 0.9, which is equals to 0, we will put, so we get z equals to 0.9. So we have got that we have a pole, roots of the denominator denotes the position of the poles. Okay, so we have a pole at 0.9, no complex numbers, that means in the real axis. Okay. However, if I have to implement the filter, for the implementation, what I said, what are the operators? There were three operators we discussed. The first operator was delay operator, which is basically z inverse. So and yeah, and next was the multiplier, and the third operator was adder. Okay. So if you see here, there is a multiplier. This is basically adder. We can write plus of minus of 0.9. We can write it, right? So it goes into the adder, this minus sign, and what is left? This z inverse, which is basically will give you the delay. So while you are implementing the filters, we have to use the Z inverse equation. If it is not there in the Z inverse terms, you have to convert it into the Z inverse terms and then proceed with the numerical. Okay. Now comes, I have given you the system. What is the order of the system? Basically, it is told the order of the system is given by the fact the highest order of the maximum of the highest order of the numerator and the maximum of the the highest order of the denominator. Okay, so maximum of order of numerator and order of denominator. So we need to look into the order of the numerator and the denominator, and based on that, the maximum of whatever we get, that maximum value would be said that this filter or this system is of that order. Okay, but for our filters, what we have discussed, filters and systems which are LTI systems, we have discussed that the number of poles should always be greater than equal to the number of zeros. That means whatever is the order of the denominator, that would be the order of the order of the LTI filter of the system. Okay, that you need to remember. Now, how to convert this equation to the Z inverse equation? First, you have to find out the order of the system, and then Z to the power minus of that order. In this case, the order is 1. So, hence we multiplied the numerator and denominator with Z to the minus 1 in both the numerator and the denominator. If it would have been, say, Z square minus of 0.9, then this would have become Z to the minus 2 and divided by Z to the minus 2. Okay. So you need to find out the order of the denominator, and after finding out the order of the denominator, we have to multiply the numerator and denominator with Z to the power minus of that order, both in the numerator and the denominator, to get into the transfer function where which can be used for the implementation of the system. Okay. Now we are given with this system. Now I ask you, find out what is the amplitude response of the system. Okay. So for doing this, we will take 5 points. We will take 5 points: 0, pi by 4, pi by 2, 3 pi by 4, and pi. Okay. So modulus of hz at 0 is, numerator is 1, डिनोमिनेटर ये 0.9 में है. So distance of the pole to the frequency point is this one. So radius is 1, so 1 minus 0.9 is 0.1, so it comes out to be 10 at 0. Amplitude value is 10. And similarly, if you look in pi, this is 1, this is 0.9, so 1 by 0.9, I think it is somewhere in 0.5, approximately 0.5, right? So we get 0.5. So what about in other these factors? How to find out? Okay. So just drawing this one. We have the pole over here. So what we can do, this is known to us, this angle is known to us, we can calculate this distance. Okay. So say for example this is A. So this distance is 0.9. So what will be this if I just draw it over here? What will be this distance? 0.9 minus A. Okay. You get this one. You have this perpendicular value already calculated. What is this hypotenuse? That would be the distance of the pole to this here. So you can find out this point. What should be the amplitude value? Okay. Next is here. We know this is 1, this is 0.9. It's simple that you calculate this value. Okay. Done. I am erasing. Now next is here. We want to find out this distance. This is just the mirror image of this one. So A, what we have calculated here also, this is A, right? कुछ समझ में नहीं आ रहा है तो please ask me. If you are not able to get me, please ask me. Okay. This is A. This is 0.9. A plus 0.9. This already you have calculated from here, right? The perpendicular distance you have already calculated. So you can calculate the length of the hypotenuse. Okay. Now, if you want to find out the phases, let's start with this phase. We need to find out this to this, but we cannot directly find out. So we have this triangle. So in this triangle, we need to find out this angle. So if you see, yeah, base by hypotenuse is the cos. Perpendicular by base is yeah. You remember this formula? Pandit Badri Prasad har bole. Okay. So P by H is sine, B by H is cos, P by B is tan. So we have the base and hypotenuse. So if you have this base and hypotenuse, you can get this angle. So when you get this angle, 180 minus this angle, you get the thing. Here also, this is a right triangle. You get this angle, you will be able to do this. Similarly, for the first one also. So in this way, you will be able to get the amplitude responses and the phase responses. Okay. At 0, what will be? Parallel line will be 0. It does not have to move. So at 0, it should be 0. At pi, it is pi. But if you see, it is a pole. So there should be a minus. Right? So at pi, it should be minus of pi. Okay. So whatever the value you are getting, you have to put in a negative sign. Okay. Now herein I have given you say 0 degree, pi by 4, pi by 2, 3 pi by 4 pi. Now I may say you that fs equals to say 200 hertz. Now then I tell you, you find out the amplitude and the phase response. So what you have to do, you have to plot in terms of frequency and not 0, pi by 4, pi by 2, 3 pi by 4 and pi. Okay. If sampling frequency is given, you need to find out for this 5 location, but then you convert this into the frequency components. Okay, that you will be able to do it. I have already told you how to do that, so I hope you will be able to do that thing. Okay, so please do it. Um, then we can discuss. So uh, we can discuss it tomorrow. So we'll start with the filters in the next class, digital filters. Hmm. Pi by 4? Ah. Ah. Yes. Ah. Ah. Hmm. Hmm. That's what I told you. You need to find that thing. So you have this say circle, you have this one. If you have this one, so this is A, this is at 0.9, 0.9. Now I am just increasing, magnifying this part. This part is being magnified. Okay, here you want to see. Here you have got. So what is this component? 0.9 minus of A, right? So from this main this thing, this is one. So as you told you, 1 by root 2, use Pythagoras theorem or any of this to get the perpendicular. P by H, you know the hypotenuse, it is sine theta. You know the theta, you know the hypotenuse, you find out the perpendicular. Pi by 4. Ah. No, no, I am talking about this triangle, na. So this perpendicular and this perpendicular are same, na. Huh? So this perpendicular are same. So if you find out this perpendicular, you get this perpendicular value. And if you, yeah, this one is 0.9 minus A. So just Pythagoras theorem you apply, you get the hypotenuse. Okay. Anything else? Similarly over here also, you know this length, This perpendicular value यहाँ पे जो ये किया है, since they are mirror images, the perpendicular distance would be the same. It will not vary. So यहाँ पे आपको this one you got, this is the hypotenuse. You already calculated from here the A value. So this is A, this is 0.9. So you got the total length, you got the perpendicular, you just find out the hypotenuse. Okay. And then you find out the phases. 180 minus whatever angle you get, you just try to do that, you will easily get that. So this is the mechanics of how the amplitude response and phase responses they are being calculated. Okay. So slowly we will be going into more in-depth